Alright, so what the current division rule says is that whenever you're having a current approaching a node or a junction, it splits. And then it doesn't just split equally or evenly, it splits based on the resistances in the branches that it's going to. Right, so let's see. Alright, so this one right here, this is the voltage source, right? Positive, negative, current goes in this direction. And this is the current from this voltage source, right? Okay. You understand this? We will move on. Here we are not going to prove it, how the equation works, but then we are just going to see the relationship and then use it. Okay. So this is the main current, and then when it gets to this node here, it splits to this I1 and I2. So basically, this means that I1, right? This means that I is equal to I1 plus I2. That's what it means, right? Yeah, because it's split, and this basically Kirchhoff's law, right? Yeah. Okay, so now we are going to see the relationship when we are trying to find a divided current or something. So it says that if you are trying, let's say you are trying to find the current I1, right? If you are trying to find I1, we clearly know that I1 is a portion. I1 is a portion of I, which is the full current, right? So basically, I1 is directly proportional to I, right? Okay, the same thing, I2 is directly proportional to I, right? But then this is how the relationship itself is the fourth thing, right? There's a proportional sign, but meaning we have to introduce something, right? So this means that the actual thing is I1 is equal to I, right? And then what did we see? We see that when the current I gets to this node here, it splits, right, to I1 and I2. And it doesn't split what evenly, it splits based on the resistances here. So meaning that the formula has some portion, a portion that have the resistances, right? That helps in the division. So this is what it means. So I1 is this how it's done. It's a proportion, right? So I1 is a portion of I. So I comes, and then what gives us a proportion, right? The fraction that gives us a part of I, right? So that's how it goes. You see, if you are trying to find I1, right? I1 passes through R1, right? This I1 current here passes through R1, right? So this I1 here passes through R1, right? And then this I2 passes through R2. So this is how it goes. So if you're trying to find the current I1, it's basically I times the other resistor, right? It's a fraction though. So the other resistor, which is R2, right? And then the sum of the resistances, right? The ones that it branches to, the ones that the main current branches to, right? In this case, just two resistors, right? So that's R1 plus R2. So this is how the basic relationship is, right? We know I1 is directly proportional to I, but then there's a fraction, right? So I1 is equal to I times R2 on R1 plus R2, right? So remember this, you are trying to find I1, meaning that we know I1 is a portion of I, clearly. The next thing to know is that if I1 is here, the one that we put at the top will be the R2, right? The other one that the I1 is not passing through it. This clearly means that if you're trying to find I2 is equal, this proportional is not important, but just for us to understand what's happening, right? I2 is proportional to I, right? So we now we have I2 equal to I, we have something multiplying it, right? The fraction. So we are finding I2, meaning that the current at the resistor we use here will be R1, right? So now we have R1 here plus R2. So basically that's how it works. We are not proving anything, we're just seeing the logic behind it and how we can apply it, right? So we try an example. So let's see. Okay. So here the aim is for us to find I1 and I2, right? So this is how we go about it. But then it's very important that when you are doing second analysis, you pay attention to the directions given. I mean the direction of the quantity, especially the current, right? So looking at this clearly, you see that this I1 here, the current direction is this way. This I2 here, the current direction is this way, right? So you use everything there. But then if after everything, you calculate everything, then you see a negative, it means that that thing is supposed to be in opposite direction to what is given, right? That's what it means. It's not anything different, right? So let's see. Because here we are going to do some calculations, we will need a calculator. All right. Okay, so now let's go on. So now we know the relations, right? The relationship we are supposed to use in to solve this, to get this problem solved. So if you are trying to find I1 is directly proportional to this 10, right? So then again, this what I'm writing here, this proportionality is something that's very important, but for us to understand what's happening, right? Directly proportional to this 10 amperes, right? So that will mean that I2, sorry, we're adding I1 first. So I1 is equal to 10 amperes times, right? So we know I1 here passes through the 3, meaning that we use the other one as the numerator. So that will be 2 on 2 plus 3, right? And yeah, 2 plus 3. There's a fraction because here we end up getting resistance here, and this together resistance cancel, meaning here is yeah, just a number, a fraction, right? So a portion of the 10 amperes. So let's see what we have for that. We have 10 times 2. This are also let's take them out. Okay. Right. Then we have 2 plus 3, right? And that gives us I1 as 4 amperes. So that's what we have. I2 the same way, right? So 10 is a portion of 10 of the 10 amperes, right? And then if we are trying to find I2, we use the other resistance, right? The one that the I2 is not passing through. So that's the 3 amperes. 3 ohms. So that's 3 ohms. 3 on 2 plus 3. The same thing, but slightly different. We have 2 plus 3. And that gives us 6 amperes. So clearly you see that when we add these two, this and then this, it gives us the 10 amperes that we have here. So it follows the logic that we were seeing that at that particular point, that's Kirchhoff's law, the current branches or split based on the resistances in the branches that is going to, right? So that's what we have. Another example. So let's see. And then after this, we'll do something, a slight adjustment and see if we understand what we're actually doing. Oh, I think there's a problem here. Then again, we didn't pay attention to the direction, right? Yes, up. Yeah, so we should have looked at that. So that clearly means that you have to pay attention to the direction, right? So because we are using this voltage here as our reference, this one here as our reference, meaning that this one is our reference here, right? This direction is our reference. Anything that opposes this one becomes a negative. So right here, this 10 here is plus because it goes in the direction that we have chosen. This I1 here goes in the direction that we have chosen, but this I2 goes in the opposite direction, right? So that will mean this will happen. That we'll have let's see. Okay, this I1 is okay because it's in the same direction. Let's see, I1 is okay because it's in the same direction as the 10 amperes, right? But I2 no, it's in the opposite direction. So that will mean that we have negative I2, or just forget that one, and then we just put a value here and we say negative I. Just a negative I. Then again, this doesn't mean that when you add this up, it is not 10. When you add the absolute values, it's 10. Right? But just that this negative here is just showing the direction, saying that this actual the direction of this actual I2 here should be in the opposite direction to what it has been given. So this means that the actual direction for the I2 is this, right? It's down and not up. This is not the right one. Right? So yeah, that's what it means. If you see something like that, doesn't mean it's wrong. It's just the negative is just telling us it's in the opposite direction to what we started with. That's all. That's the only difference. Yeah. So with that clear, we go on to the next example. So let's see. Okay, example 2. Okay, so here we're trying to find, looking at how it is, our interest is just trying to is just to find the I1, right? Okay, and then we know that the current division, basically looking at how the formula is, it only considers 2 resistors at the time. Let's look at this. Okay, so we know if the current is moving from this here, from this voltage source, it gets here. When it gets to this node here, a split. So we have one here, and so we can have something like let's see. We have something like, let's see, I2 here, right? And we have something like I3 here. But from the look of things, our interest is just the I1, right? So that's why that one is in good. But then the formula, how the formula is, so this how it is. You're trying to find a particular, see, the current in a particular branch. So what's it? We're trying to find the current in a particular branch. So let's see this. Let's use this. So we're trying to find the current in a particular branch, right? You multiply by the main current is equal to the main current, then multiply by the resistance, right? So looking at this, it's just two resistors involved. So this gives you the idea that when you get something like this, you're trying to find this, you kind of have to consider this, like simplify it to get just one, right? And clearly, looking at how this one is, these two here are in parallel. Okay, those two here are parallel resistors, right? Why? Because you can go across them without passing through any other element, right? So you can simplify it and get one, and then straightforward you'll be able to use the current division, right? So let's see. So this will mean that this circuit here is simplified to something of this sort. We have this, right? Just using this blue. So we have just this here, and we have just this here. What this will be, or this 2 in parallel with this 3. So 2 in parallel with 2 ohms, right? And here we this 3 ohms, right? Here with the voltage source, right? Right. So this is how to simplify to. Okay. So we are going to go straight and do it. So now that we have this we are trying to find the value for what is here. This here means 2 and 2 resistors in parallel, right? So this is how we go. So if you are trying to find the resultant, right, or the effective resistance or the parallel one, this is how we do. That's product over sum, right? So we're trying to find whatever is here. This 2, this 2 parallel 2 resistor, the value with this 2 times 2 over sum, that's 2 plus 2, right? So that gives us a 4 and 4, and that's a 1. And then for these things, it's better you just point them because you know the procedure. Instead of thinking through it, you might skip something so that you get more energy or more space to think through the things you might think through. You have a calculator by you, so why not? So this gives us 2 ohms. Sorry, that gives us 1 ohm. So that's 1 ohm that we have here, right? So now that we have this, all this changed to 1. Right, so this here is 1 ohm. And then it's not always that you have to draw everything. You just have to understand the concept. When you see it, you know what to do. Go straight forward to the point. This for understanding, that's why we write a lot of things, just so that we understand and then we follow what we are doing. Right. Okay. So if we are trying to find the I1, which is here, right? Okay, 1. Okay. This will mean that I1 is equal to is direct proportional to the 10 amperes that we see here. So that's 10 amperes, and then we have a fraction, right? Now we have 2 resistors. We can do it straightforward. Because we're interested in this one here, the numerator will be this, right? So that's 1 all on 3 plus 1, right? Yeah, 3 plus 1. So that gives us, again, you can punch it straightforward. You have a 1 on 4, and that gives us the I1 as 2.5. The unit is very important. All right, so now we're going to look at something very subtle, but then you understand that whenever, however the problem is, you're able to do it. So imagine this, that we have another wire here, right? Another wire here connected this way, but then it has no resistor attached. There's no resistor, just a wire. What does this mean? This means that we've connected a short circuit here, right? So the current that comes from this, the current from this, right, won't go to any of these, right? Why? Because there's what we call a short circuit here. So definitely this current here moving from this voltage here will prevent what we call in quote soft light, right? It doesn't want any resistance. That's the best part it would like to go, right? Because these guys will reduce it, right? To reduce it, right? So clearly it will want to go straight forward and pass through this one right here. Because this is the least resistance part, right? So to use that one, no resistance at all, soft life, right? Yeah. So the same will happen. So let's see for this one, right? Let's say we manage how the circuit is in a slightly different way, and then we have something of this sort. Let's see. something here, short circuit here, meaning that all the current will definitely flow. This whole 10 amperes here will flow through this. It will definitely skip this one. So the current through this 3 ohms here, right? The current through this 3 ohms here will be 0. So it will end up, because we have this short circuit here, we end up having I1 to be 0. That's if we have the short circuit there, right? So that's it. But then there's one thing that we're going to do. We've said that in applied electricity, the basic equation that we are following is V is equal to what? IR, right? Yeah. So now right now we are doing current division rule, and then our aim is, our focus is on this, right? Okay. And then looking at this one, we see that clearly the current division happens when the circuit are in parallel. So looking at this one, for instance, because when the current gets to this side, let's clean this up. Okay. So when the current gets to this side, this node here, the current gets here, it splits to this, and then this, right? And you see that these three here are in parallel, right? So yeah, okay. We get to this one, to the same thing. This example, the current gets to, let's take this one off. Okay. When the current gets to this side, the side where we have the I1, right? So when the current gets to this side, it splits and gives us I1 and I2, and clearly we see that these two resistors are parallel. But when it comes to current, let's see. So we said the basic equation in applied electricity is V is equal to IR, right? So what it says is that when one element, we are going over this one more time. One element are in series, the current flowing through them are the same. So if you have one resistor here, have another one here, and then the current is coming from this side, the same current will reduce. It will flow through this and flow through this. So if I have a current of, let's say 2.5 amperes flowing through this, the same 2.5 amperes will flow through this, right? Why? Because they are in series, right? That is it for current. So that's how. So when they are in series, the current are the same, but when they are parallel, or there's a junction, they are joined at a junction, there will be a split, right? But something similar happens to the voltage, right? But slightly different. So we are going to look at that later. So that's what we have. So think about, what do you think will happen, right? So when it comes to the voltage, it's a bit different. So now that we have the current rule, we also have the current division rule. We also have the voltage division rule. This is the current division rule, but for this one, the voltage division, the name is slightly different. We see a voltage drop, right? So, all right.